All right, folks, it's time for a bit of an exam review. We're going to take exam 5 soon, and remember that's going to be on states of matter as well as solutions. So we're going to chop this review into 2 halves. The first half will deal with states of matter. Now, for some of these things, I'm just going to refer you to page numbers in your manual. So, for instance, you should know properties of gases, properties of liquids, and properties of solids. Review those before the test. Now, those are on pages 91 through 93 of your manual. Okay? Should also be able to do simple things like this. If I asked you to draw 10 gas particles, liquid particles, or solid particles, what would they look like? So if I were to draw 10 gas particles in this square here, labeled gas, I'd just use spheres to represent them. So we have one, and we'd have another one over here. You know, they occupy the entire volume of their container. They don't have any particular organization at all. So what do we have so far? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and you know, they're constantly moving, bouncing off the walls of their container. They can flow past one another, and they have huge distances between one another. So even though I've drawn them relatively close together in this illustration, in reality, there would be huge distances between neighboring particles. So I'm just going to write huge distance between neighboring gas particles. They can be compressed. Now, liquids, on the other hand, they don't really have an organized structure, but they do have a definite volume. They take the shape of their container. So if I had liquid particles, I'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. They really wouldn't have a shape. They'd be really, really close to each other. They can flow past one another, but they're much, much closer than gas particles. Now, how are solid particles different? They have a definite shape, don't they? And so they have this organized pattern that we call a crystalline lattice. So if I were to draw 10 solid particles, I might end up with something like this, where they're really, really close together. What is that? 8, 9, and 10. They're really close together and have a definite structure or shape to them. They can't be compressed, and they can't flow past one another. So just be familiar with basic properties of gases, liquids, and solids, and just be familiar with, if you could see those particles, what they might look like as far as being spread out in their container. All right, next one, number 5, what are the postulates of the kinetic molecular theory? So review page 91 of your manual, where I go through 7 basic parts of the kinetic molecular theory. I don't expect you to memorize them, but you should be aware of the postulates of the kinetic molecular theory. We also talked about this concept called equilibrium, which actually is going to be an entire chapter in the near future. So make sure you guys know what dynamic equilibrium is. Let me just go through something very briefly. If I had H2O in its solid phase, and I had it turning into H2O in its liquid phase, now you should know that that's an endothermic process. To go from a solid to a liquid, energy is required. So I'm going to put the symbol delta H on the left-hand side. And at 0 degrees Celsius, what is water doing? Is it doing this, going from a solid to a liquid? Yeah, most of you folks understand that that's melting at 0 degrees Celsius. But you also understand that at 0 degrees Celsius, water freezes. So it's actually going back in the other direction. And when we reach equilibrium, the rate of the forward reaction, in this case, water going from the solid to liquid phase, or melting, is equal to the rate of the backwards reaction, which is water going from the liquid to solid phase, or freezing. Okay, you should be familiar somewhat with Le Chatelier's principle. Remember, if I place a stress upon this system will react to relieve the stress. So for instance, let's say that I'm adding heat to this system. The system would move to relieve the stress by going away from the heat. So remember, delta H is our symbol for heat. So if I increase the temperature, we would say the system would shift towards the product side to get away from that heat, and of course more liquid would form. If you decrease the temperature, it would go towards the heat, and more solid would form. We also talked about changing pressure, and if I were to increase the pressure, it would go to the side that occupies the smaller volume. And water is really peculiar in that the liquid has a smaller volume than the solid. So if I increase the pressure at a temperature, let's say below the freezing point, water could melt. It would go to its liquid phase. And we know how we talked about ice skating and the pressure below the surface of a blade and how that increases the pressure and as a result melts the ice below. So go through those couple of pages, 99 through 100 in your manual, related to dynamic equilibrium. Okay? All right. How about this one? This relates to the kinetic molecular theory. If two molecules of different masses are at the same temperature, do you remember which one travels faster? Yeah, they have the same kinetic energy so long as they're at the same temperature, so their kinetic energies are equal. If they have different masses, though, remember the smaller molecule will have the greater velocity. That needs to compensate for its size, so it needs to move faster so it can have the same kinetic energy as a large molecule. All right, number 8, do you remember what a particle needs to have or be in order to evaporate? Yeah, there are two criteria. Number 1, it needs to be on the surface, doesn't it, of the liquid. And number 2, it needs to have enough energy, and I'll say kinetic energy, to escape the attractive forces of its neighbor, right? Or neighbors. So to escape attractive forces of the neighboring molecules. So if it has enough energy, but it's at the bottom of the beaker, it's not going to be able to evaporate because it's not on the surface. But if it's on the surface and has enough energy to escape the attractive forces of the neighboring molecules, it can evaporate. And remember, evaporation is a cooling process. The high energy molecules leave when they evaporate. That always leaves behind the lower energy molecules. Yet, a glass full of water, if left undisturbed, will eventually all evaporate. And that's because eventually molecules will end up on the surface and they will get energy from their surroundings to be able to evaporate. All right, make sure you review how atmospheric pressure affects the boiling point of a liquid. Remember, as the pressure decreases, so as pressure gets lower, the boiling point decreases as well. There's less pressure, so it's easier for those molecules to separate from one another and turn to the gaseous phase. So we talked about why here in Salt Lake, the boiling point of water is less than 100 degrees Celsius. While at sea level, where the atmospheric pressure is higher, the boiling point is 100 degrees Celsius. And of course, if you go below sea level, let's say Death Valley, where the pressure is higher than at sea level, the boiling point would be higher than 100 degrees Celsius. So review that section of your notes as well. Number 10, do you remember what it's called when something changes directly from a solid to a gas? Now, I could put questions like that on the test, and of course that's called sublimation. How about the opposite, when it goes from a gas to a solid? I'll let you look that one up on your own, okay? All right, next up. Remember hydrogen bonding, and we also talked about network covalent bonding. We talked about dipole-to-dipole interactions, and we also talked about London dispersion forces. Well, I want you in the space below to draw two water molecules. Draw their Lewis structure. Then after you do that, identify the covalent bonds within the water molecules, and also identify the hydrogen bonding between the molecules. See if you can do that. See if you remember how to do that. I'll give you a second. Okay, here's the Lewis structure for a water molecule, H2O. Remember, there's a bent molecule, so I'll draw it like that. And we have a very strong dipole here. In fact, it pulls this electron pair away, or electron away from hydrogen, and it surrounds the oxygen most of the time. So these hydrogen ends have a very positive charge. They're bare protons, remember? And the oxygen end has a very negative charge. So if I had another water molecule, wouldn't the neighboring molecule orientate itself something like this? So the positive end of one molecule is attracted to the negative end of the other. And so the hydrogen bond would be the bond between the water molecules. So this would be what we would call the H bond. And then those blue lines, that's where electrons are being shared. These would be covalent bonds. So this and this, that would be, or those would be covalent bonds. And here, we would also have covalent bonds. So remember the difference between intermolecular forces, that's between the water molecules, and intramolecular forces, which is within a molecule. All right, number 12. Let's see if you guys remember how to do this. What's the chief intermolecular force of attraction between the following molecules? Here are our choices. We have dispersion forces, which we like to call LDFs for London dispersion forces. We have dipole to dipole, don't we? We have hydrogen bonding. We have network covalent bonding. And we have ionic bonding. There's also metallic, which we're leaving off of this test for you. So let's take a look at O2. If I were to draw its Lewis structure, you would know it looks like this, and it's a non-polar molecule. So that rules out dipole to dipole, doesn't it? Of course, hydrogen bonding is ruled out as well. Network covalent's really specific. If we have diamond or graphite or silicon-containing compounds, we would see network covalent. And it's not ionic because we don't have a metal to a nonmetal. So oxygen molecules are held together by London dispersion forces. And as a result, that's a weak intermolecular force of attraction. It's a relatively light molecule, so it would have a low melting and low boiling point. H2SE, let's draw that Lewis structure. It looks like this. It's bent just like the water molecule. And there's a difference in electronegativities between the hydrogen and the selenium. And so we have the electron pairs being pulled towards the selenium because it's more electronegative, so that has a negative charge on that side of the molecule. And these hydrogens have a positive charge on that side of the molecule. And so we would call this dipole to dipole. And it's a polar molecule. And so if we threw a bunch of those in a box, they'd clump together, we would expect, like tiny magnets. All right, how about C2H5OH? This has hydrogen bonded to an oxygen. Do you remember? Yep, those guys can hydrogen bond. So in order to hydrogen bond, the hydrogen on one molecule needs to be attracted to the oxygen end of another molecule. Graphite, I gave that away earlier. It's just carbon atoms, but the melting and boiling point is super high, so LDFs can't account for that. So that must be network covalent, where the carbon atoms are actually held together by covalent bonds within a layer. And between the layers, they're held together by London dispersion forces. So graphite, we can split those layers up fairly easily, but within the layer, it's hard to tear those carbon atoms apart. And the last one's pretty easy. We have a metal, calcium, and a non-metal, chlorine, so that would be an ionic interaction. Okay? All right, let's go to the next page now. Oh, we have some phase diagrams here. So let's see if you guys remember how to do phase diagram work. So for 14 through 16, we're going to use the term sublimation, condensation, vaporization, melting, or deposition. So let's take a look at this phase diagram. And we have the pressure decreases from 1.5 to 1/2 of an atmosphere at 50 Celsius. So here's 50 degrees Celsius right there. Here's 1.5 atmospheres, and we're decreasing that at the same temperature to 1/2 of an atmosphere. So it looks like we crossed that line. I wonder what line that is. Do you remember? Yeah, this is the solid region, this is the liquid region, and this is the gaseous region. So number 13, we're going from a liquid to a gas. What's that called? Yeah, if you said vaporization, so the answer for 13 is C. If you said vaporization, that's correct. It would boil right here at that temperature and pressure. Okay? All right, how about from 10 to 50 degrees Celsius? So we're going to go from 10 to 50 degrees Celsius at a pressure of a half of an atmosphere. So we're going to start right there, and we're going to end up right there. So we're going from here to there. Looks like we're going from a solid to a gas. What's that called? That's right. If you said sublimation or letter A, you are correct. It skips out the liquid phase. Once we get below that triple point, we don't have the liquid phase any longer, do we? Okay, how about number 15? We have the temperature decreasing from 110 to 40 Celsius. So we're going to decrease from 110 down to 40 Celsius at a pressure of 1.1. So 1.1 is going to put me right about there. So I'm going to start right about there on, oh, sorry, let's erase that and get a little better point here. So I'm going to start right about there, and I'm going to go down to 40 degrees Celsius at that same pressure. So I'm going to go all the way down to 40. We're going to end up right about there, aren't we? So gas to a liquid. What's that called? That's right. If you said condensation, you got it. Alrighty. Now there are some other things about a phase diagram as well that we'll talk about. Let me skip down to 17 really quickly. Make sure you know what a triple point, normal boiling, normal freezing, critical temperature, and critical pressure. So just a heads up, we're going to do that right here at the end of this first review. How about number 16? Do you guys remember MCAT problems? Yeah, remember Q, the heat required or released during a temperature change is equal to the mass times the specific heat, which we abbreviate with the letter C, times the temperature change. And so if I have a 15.75 piece of iron, it absorbs 1,086.75 joules, and the temperature goes from 25 up to 25 to 175 Celsius. How much heat does it absorb? Sorry, not how much heat does it absorb. We want to calculate the specific heat, sorry, because we know how much heat it absorbs, don't we? So we're going to solve for C, which is the specific heat, and that will be equal to Q divided by the mass and the delta T. I'm not going to do the math for you. I think you can take the time to do that, but let me plug in some numbers for you. Q for this is 1,086.75 joules. The mass of the object, remember, 15.75 grams, and the delta T is the difference between 175 and 125. So we're going to go from 25 to 175 degrees Celsius. And our unit, we would end up with this joules on top and grams and degrees Celsius on the bottom, and that is our specific heat unit. So you can do that math on your own, and you will get the specific heat of that metal. Okay? You should also be able to solve for Q if I give you the mass, specific heat, and delta T. All right, so the last question on our review, I want to take a look at these two-phase diagrams. One's for water and one's for carbon dioxide. And I want to talk about triple points first. Triple point, remember, is when we have the solid, liquid, and gaseous phase all in equilibrium with each other. So I'm going to highlight that in green for you here. That's the triple point for water. Looks like it's at a temperature of 0.0099 degrees Celsius, pretty close to zero, and a pressure of 0.006 atms. For CO2, there's the triple point. Looks like the temperature is about negative 56 degrees Celsius and a pressure of about 5 atmospheres. Okay, all right. How about the normal boiling point? Remember what the word normal means in this context? Yeah, it's 1 atmosphere of pressure, 1 atm of pressure, or 760 millimeters of mercury. So normal boiling, we're going to be looking at the liquid gas equilibrium. And so there's 1 atmosphere. We're going to go from a liquid to a gas. Put it right there at 1 atmosphere, and that is 100 degrees Celsius for water. Now, CO2 does not have a normal boiling point, does it? Yeah, if we go to 1 atmosphere, we come across to the liquid gas line. We don't bump into it, do we? We go directly from the solid to the gas, so it sublimes. How about the normal freezing point? Yeah, that's the liquid-solid equilibrium line at 1 atmosphere. So at 1 atmosphere, if we go and we bump into the liquid-solid line, it's going to be about, well, it will be 0.0 degrees Celsius for water. For CO2, does it have a normal freezing point? Nope, it doesn't. We don't have a liquid-solid equilibrium at 1 atmosphere. Once again, we just have the solid or gaseous phase. Critical temperature, remember, is the temperature above which no amount of pressure can liquefy a gas. Let's change colors here. So in my phase diagram for water, once I reach the critical temperature, this line just goes up forever because no amount of pressure can turn that substance back into the liquid phase. It will always be in this gaseous phase above the critical temperature. And the critical pressure for water is 218 atmospheres. That's the pressure needed to liquefy a gas when it's at the critical temperature. Not above, though, because remember, it can't be liquefied above the critical temperature. And then for CO2, it looks like the critical temperature is 31 degrees Celsius and the critical pressure is 73 atmospheres. So once you get there, once again, this line goes straight up, 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 and we're just going to have the gas phase above 31.1 degrees Celsius, no matter how much pressure we add. Okay? Well, that takes care of the first half of our review. That's on states of matter. This was a little bit longer of a review, but I think you guys need it. It's been a while since we've talked about these things. So please go over those important things in your notes that we've talked about and be ready for the test next time. Okay? See you soon. Bye-bye.